The universe often hides its deepest truths inside things that feel impossible. Quantum entanglement is one of those things. It is the strange connection that startled Albert Einstein so deeply that he called it spooky action at a distance. Imagine two tiny particles born together in a single event. They then fly apart, one traveling to the left side of the cosmos and the other to the right. They may be separated by a distance that would take light billions of years to cross. Yet if someone measures one particle and discovers a particular property, such as the direction its tiny quantum spin points, the other particle will always respond in a perfectly coordinated way. Not sometimes, not most of the time, always. It is as if the universe whispers to the second particle instantly. Einstein hated that idea because he believed nothing could influence anything faster than the speed of light. To him, it seemed like a secret signal must be racing between the particles. But if such a signal existed, it would need to travel faster than light. That would break the most cherished rule of relativity. Einstein proposed that maybe the particles carried hidden instructions from the moment they were created, like matching envelopes that simply wait to be opened. The universe would not need any faster than light communication if everything had already been decided. For decades, scientists argued fiercely about this puzzle. Was the quantum world secretly deterministic, following rules that no one had discovered yet? Or did nature truly behave in a way that ignored classical ideas of locality? Then came a breakthrough from physicist John Bell in the 1960s. He crafted a clever mathematical test. If hidden instructions existed, then certain patterns of measurement would never appear. But if spooky action was real, those forbidden patterns would show up. The experiments that followed were bold. They used photons of light sent in opposite directions, sometimes across entire buildings, sometimes into the open sky. Each time, physicists tested the results against Bell's predictions. And each time, the universe chose the spooky answer. Local realism, the comforting notion that objects have definite properties independent of observation and that nothing can influence anything faster than light, could not explain what was happening. The quantum world behaved as if the particles remained one system, no matter how far apart they traveled. But this astonishing connection has a limit. It does not let anyone send a message faster than light. If two people each hold one member of an entangled pair, neither can control what outcome their measurement will give. They only discover the correlation after comparing their results later through a normal, slow, light-speed communication channel. Entanglement creates perfect correlations, not a telegraph. It is a connection without a signal. This makes entanglement even more mysterious. If it is not a force pushing or pulling, if it is not a message sent between the two particles, then what is it? A change here is reflected there without anything traveling between them. It is as if the universe refuses to separate the two particles, no matter how far they are dragged apart. The separation we imagine in space may not be the true separation in the deep mathematical structure of reality. Scientists sometimes describe entanglement as a kind of quantum bookkeeping. When particles interact, they share a wave function, a unified description that encodes all possible outcomes at once. When they separate, that wave function does not split into pieces. It stretches across both particles, binding their fate. Space tells us the particles are far apart. Quantum theory tells us they are still part of the same story. There is something comforting in that thought, as if the universe holds long-distance friendships together with invisible ties. But there is also something unsettling. Our everyday intuition breaks down. We want to believe that objects have their own independent identities. We want to believe that effects have clear causes in clear places. Entanglement laughs at those hopes. Quantum theory insists that what is real is not located neatly inside space. Instead, relationships are primary. The world is a network of connections, an arrow pointing from one particle to another, a shared history that refuses to fade. Entanglement reminds us that the universe is less like a set of separate billiard balls and more like a single tapestry, woven so tightly that pulling a thread at one edge makes the entire fabric shift ever so slightly all the way across. Even calling entanglement strange is a confession. We are measuring the universe against our human expectations and finding it wanting. Nature does not promise to make sense to us. Nature only promises to be consistent. And entanglement, as bizarre as it feels, is one of the most consistent features of quantum physics. Every test has supported it. Every loophole has been closed. Yet Einstein's objection still echoes. If there is no signal and no force, how should we think about this connection? How can two pieces of matter remain parts of a single entity, even when space-time itself stretches between them? There is a transition coming. Entanglement obeys the rules of quantum mechanics. Gravity shapes those rules through the geometry of space-time. For more than a century, the two realms have refused to blend. Before we confront their relationship, we must understand them separately. We have explored the quantum link. Soon, we will face the weight of space-time and ask whether this strange connection could reach into the deepest structure of gravity itself. Quantum mechanics teaches us that measurement is not a gentle glance. It is a physical interaction that leaves a mark on the system it touches. When we measure an entangled particle, we collapse a wide range of possibilities into one concrete reality. That collapse ripples instantly through the shared wave function. Not as a wave traveling through space, not as a signal carrying information. Instead, it is as if the universe updates a single story that always included both particles at once. The change is global, woven through the entire quantum state. This idea makes many people uneasy. It challenges the comforting thought that space separates objects and that nothing can leap across the gap without time. But entanglement hints that quantum reality might not be written inside space at all. Instead, space might be written inside quantum reality. This raises questions we are only beginning to explore. What if distance is not a fundamental feature of the universe? What if space is an emergent illusion born from deeper relationships that operate beyond location? Physicist David Bohm once used a powerful analogy. Imagine a fish inside a tank, filmed by two cameras from different angles. A person watching the two monitors in a separate room might believe there are two mysterious fish that copy one another. When one turns, the other turns. When one rises, the other rises. It would seem like a magical connection. But there is only one fish. The separation between the two screens exists only in the mind of the observer. Bohm suggested that entangled particles might be similar. What we see as widely separated things could be different views of one unified reality. Still, physicists are strict. We do not accept metaphors without mathematics, and the mathematics is clear. Entanglement is a measurable resource. It obeys rules called quantum information theory. It has a quantity that can increase or decrease depending on how systems interact. It can be destroyed by noise or decoherence. It can be distilled and strengthened if treated carefully. It is as real as energy, as real as momentum. But does that mean it has physical influence? Or is it only a map of possibilities that exist in our knowledge? This confusion leads to a subtler truth. Entanglement does not live in objects. It lives in the relationships between them. If the universe is a story, entanglement is the part of the plot that cannot be separated. Every time particles interact, even briefly, they share a bit of that plot. They carry a memory of each other afterward. And the more complex a system becomes, the more entanglement it contains. A single electron might be simple. A living brain with countless interacting particles might contain more entanglement than any supercomputer could ever properly describe. Yet for all its beauty, entanglement reveals a divide at the heart of physics. Quantum mechanics tells us the universe is built from discrete pieces operating under probabilistic laws. General relativity tells us that gravity is not a force at all, but the smooth curvature of space-time itself. These two pictures have coexisted uneasily for more than 100 years. Entanglement seems to belong fully to the quantum side of this divide. Gravity reigns over the classical side. But reality has only one side. Somewhere, a bridge must exist. Let us pause to imagine a simple case. Two electrons become entangled. Each has a tiny mass. According to Einstein's theory, anything with mass must create curvature in spacetime, even if the amount is unbelievably small. If the electrons remain entangled, does that shared quantum state also influence the curvature they produce? Could there be a subtle form of gravitational correlation that mirrors the quantum one? And if so, is spacetime itself forced to recognize the entanglement? We do not know the answer, but we can explore the questions, we can test them experimentally, and we can follow the mathematics to wherever it leads. Already researchers have discovered that if entanglement is destroyed by gravity, such as near a black hole horizon, information appears to be lost. But when we consider the entire system, including the gravity of the black hole itself, the information might survive in a more subtle form. This suggests that gravity and quantum mechanics are not strangers. They are two actors in the same play, speaking different parts of a single language we have not fully understood. Einstein once believed that the moon exists whether we look at it or not. Quantum physicists say that for microscopic objects, reality is defined through observation. General relativity claims that mass warps spacetime, whether anyone watches or not. Quantum theory claims that outcomes do not exist until a measurement pins them down. This conflict feels like an argument between two titans of truth. Entanglement stands between them, laughing quietly. There is a hint, barely visible yet growing brighter, that gravity might emerge from entanglement itself, that the structure of spacetime could arise from networks of quantum correlations. If that is true, then entangled particles do not just share information. They shape the geometry that connects them. They pull space into being. We are not ready to embrace such a vision without evidence. Theories must be tested. Ideas must be challenged. But even now, as data accumulates, we see that entanglement can persist over long distances. It can defy separations that stretch beyond the Earth itself. It is resilient and fundamental. Our journey is only beginning. We have approached the edge of the known. Ahead lies gravity, the most familiar of forces, yet the one we understand the least. Its gentle pull has guided stars for billions of years. It binds galaxies together. It shapes every movement we make, yet it refuses to behave like the other forces governed by quantum rules. As we step into the next part of our exploration, we will leave behind the mystery of quantum togetherness for a moment and turn toward the universe of curvature and mass. We will ask why gravity stands apart, and we will see whether the strange link we call entanglement might be the key that finally unlocks its secrets. The history of entanglement is a lesson in scientific humility. What began as a philosophical discomfort has grown into one of the most powerful tools in modern technology. Quantum computers rely on entanglement to perform calculations that would take classical machines longer than the age of the universe to complete. Quantum cryptography uses it to guarantee security based on the laws of physics rather than the fragility of human-made codes. Quantum sensing uses entangled systems to measure tiny influences from the environment with sensitivity no classical device could match. Spooky action has become practical action. Each application reminds us that this phenomenon is not a ghostly illusion. It is something the universe genuinely does. When two particles are entangled, they do not carry secret notes written at birth. They are part of a pattern that can only be described by considering them together. If we try to describe each one separately, the description becomes incomplete, almost meaningless. The universe is insisting on unity. Many thinkers have wondered whether entanglement might carry some deeper message about the nature of existence itself. It suggests that separation is not fundamental. It suggests that the boundaries we draw between one thing and another are convenient but not absolute. It suggests that information, correlation, and connection may be the building blocks from which space-time and matter emerge. Of course, we must be careful. Entanglement does not allow faster than light signals. It does not break causality. It does not give us a way to communicate telepathically across the cosmos. If two observers each measure their particle, neither can choose the outcome. They only see the pattern when they later compare notes. The light speed limit still rules the movement of information. Relativity remains intact. This raises another mystery. Why would nature allow instantaneous updates to correlations, but not to choices? Why does the universe keep the marvelous part, but forbid the useful part? The answer is hidden in the mathematics of quantum mechanics. The universe protects causality by wrapping every quantum possibility inside probability. The outcome cannot be controlled. The universe never lets the connection become a conduit. Yet this boundary is not a wall. Instead, it is a clue. A clue that the true structure of space-time lies beneath the smooth geometry Einstein described. Something deeper than curved distances must hold these correlations together. Something that does not travel through space, but sets the stage on which space unfolds. There is a famous saying in quantum science: entanglement is the currency of reality. It is conserved and exchanged in every interaction. It builds complexity. It defines what can and cannot happen. In a sense, entanglement is the measure of how much one part of the universe knows about another part. When information is shared perfectly, the parts behave as if they are one. Some researchers even propose that the amount of entanglement present in a region determines the amount of space that region occupies. If the entanglement drops to zero, the space between objects could collapse. This is a radical idea. It implies that space is not the stage on which quantum mechanics dances. Instead, space is the dance itself. But we cannot leap ahead too quickly. Before claiming that entanglement builds space-time, we must understand space-time on its own terms. We must understand gravity. Gravity has stood apart from the quantum world stubbornly, almost defiantly. Experiments have confirmed that the electromagnetic force is quantum. The strong and weak nuclear forces obey quantum rules as well. Gravity alone refuses to fit neatly into that framework. The reason is simple but frustrating. Gravity is incredibly weak compared to the other forces. Only because Earth is vast and massive do we feel its pull at all. An average person can lift a small object with their hand using only muscle power. That small force is enough to resist the entire gravitational pull of our planet. If gravity were much stronger, stars might never form. If gravity were much weaker, matter might never clump. The universe would be quiet and empty. Instead, gravity sits delicately in a narrow range that allows complexity to arise. But this weakness creates a problem for physics. To observe quantum gravitational effects, we would need to examine masses so tiny and distances so small that our current tools cannot reach them. Gravity hides its quantum nature too well. The smooth picture Einstein gave us works perfectly for planets and galaxies. Quantum mechanics works perfectly for atoms and electrons. Each theory dominates its domain, but there must be one description that rules everything. That description remains unknown. Einstein's field equations describe how mass tells spacetime how to curve, and spacetime tells mass how to move. The mathematics is continuous, beautiful, and geometric. Quantum theory describes energy and matter as coming in discrete packets, governed by uncertainty and probability. When we try to combine these frameworks, infinities explode in our calculations. The mathematics breaks. The universe refuses to answer. This is where our journey now turns. To see whether entanglement can influence gravity, we must first respect gravity on its own ground. We must step away from quantum mysteries and walk into the world of curved space-time. We must understand why gravity has resisted being quantized, and we must learn why it might finally be ready to join the quantum family. In the next chapter, we will follow the path Einstein laid. We will watch how space-time bends. We will see how mass and energy shape the universe. We will ask why this force, the force that feels most familiar to us, has become the most exotic question in modern physics. And we will keep our eyes on the deeper goal: to find the place where the two great stories of reality become one. Gravity is the oldest mystery we have ever known. Before humans learned to write, before we shaped metal or painted the walls of caves, we looked up. We watched the stars trace slow circles across the night. We felt the pull of the ground holding our feet. Everything that rises must fall. That was our first lesson in physics. It felt simple, but simplicity can be a disguise. The deeper we looked, the stranger gravity became. Isaac Newton gave the world a new way to describe motion. An apple falls because Earth pulls upon it. The moon stays in its orbit because Earth pulls upon it. Every object attracts every other object with a force that grows weaker with distance. This idea reshaped science. It explained tides and comets and the turning of planets around the sun. It also raised a quiet question. How can one object reach across empty space and tug on another without anything in between? Newton himself worried about that. He called the idea absurd, even though it worked perfectly. For centuries, scientists tried to imagine invisible lines of tension or swirling substances that filled the heavens. None of these ideas satisfied. Space seemed empty, yet gravity acted through it as if emptiness were an illusion. Then came Albert Einstein with a vision unlike anything before. He did not think of gravity as a force. He thought of it as shape. Spacetime is the stage on which the universe plays out its story. Mass and energy are the actors. They press into the stage, and the stage bends under their weight. Planets do not orbit the sun because they are pulled. They follow straightest possible paths through a geometry that curves around the sun. We are held to the ground, not by an invisible hand, but because the ground pushes upward against us while space-time guides our bodies downward along gentle slopes in the geometry. This picture feels poetic, but it is mathematics that gives it power. Einstein's field equations describe exactly how matter shapes space-time and how space-time guides matter. The equations showed that gravity could slow time and stretch light. They predicted that the universe could expand, even though astronomers had not yet discovered that expansion. They predicted black holes, where gravity becomes so strong that not even light can escape. They predicted ripples in space-time called gravitational waves. Every prediction has been tested and confirmed. When the black hole at the center of our galaxy was photographed, it matched Einstein's mathematics. When gravitational waves were detected from colliding stars in the distant universe, they arrived exactly as general relativity foretold. Gravity, as Einstein described it, reigns supreme over the large scale. Yet something remains unfinished. Every other force in nature obeys quantum rules. Inside atoms, particles behave like waves of possibility. They appear only when measured. They exchange quanta of energy in precise steps. Light is made of photons. The electromagnetic force is carried by photons. The strong nuclear force is carried by gluons. The weak nuclear force by a family of heavy particles. All are part of a grand structure that follows quantum principles. Gravity is the outsider. We do not know whether gravity has its own quantum particle. Physicists expect that such a particle would exist. They call it a graviton, a tiny packet of gravitational influence that ripples through space-time. But no experiment has ever seen a graviton. Maybe it is too weak to detect. Maybe our instruments are too primitive. Or perhaps the entire question misunderstands gravity. General relativity does not treat gravity like a force. It treats gravity as the geometry of the universe itself. How do you quantize geometry? How do you break the smooth fabric of space-time into discrete pieces? If space-time is continuous, then gravity is continuous. If space-time is quantum, then gravity must be quantum. We are caught between two truths that refuse to merge. Physicists have tried to build bridges between them. One approach is called quantum field theory of gravity. It tries to treat gravity like the other forces, but when the equations are pushed to small distances, they explode into infinities that cannot be tamed. Another approach is called loop quantum gravity. It suggests that space-time is woven from tiny loops of energy. A different idea called string theory imagines that particles are not points but tiny strings. If the strings vibrate in the right ways, gravity emerges naturally from their patterns. These efforts are brilliant, but none has yet earned the authority that experiments demand. Nature has not revealed a quantum fingerprint in gravity, at least not one that we can measure today. And so gravity stands apart. It behaves classically even in situations where quantum rules should apply. It follows its own majestic logic. When we drop a ball or watch Earth orbit the Sun, it feels like everything is smooth and continuous. When we peer inside atoms, everything becomes fuzzy and unpredictable. Why should the laws of nature switch personalities depending on the size of the system? Perhaps they do not. Perhaps we simply have not found the unifying principle that explains both viewpoints at once. Perhaps gravity hides its quantum side behind a veil woven from the weakness of its pull. Or perhaps the mystery runs deeper than that. Einstein's theory suggests that time itself is not absolute. It bends. It flows at different rates depending on the strength of gravity. Clocks tick slower near massive objects. Time stretches near a black hole. Every part of reality depends on the geometry of space-time. Yet quantum mechanics suggests that geometry is not fundamental. Information and correlation may lie beneath geometry, shaping it from below. If that is true, then gravity might not only bend time. Gravity might be a story told by quantum relationships, a story we are just beginning to read. In the next part, we will explore why gravity has resisted being brought into the quantum family. We will see how the very tools that succeed so well in describing the other forces fail when they meet the curvature of space-time. And we will uncover the puzzle that leads us toward entanglement once more. Because if gravity truly emerges from the quantum world, then entanglement may be the thread that sews the fabric of the universe together. Gravity resists being tamed by quantum rules in a way that feels almost personal, as though the universe has placed a guardian at the gate of its deepest secrets. When scientists try to apply the same techniques that work beautifully for electricity, magnetism, and the nuclear forces, the mathematics of gravity fights back. In those other domains, particles exchange quanta of force, and everything remains finite and well-behaved. But with gravity, everything explodes into impossibly large infinities the moment we try to describe tiny distances or enormous concentrations of energy. It is as if space-time refuses to be carved into little chunks. The heart of the problem lies in how time and space themselves become part of the calculation. In ordinary quantum theories, space is a background. It is a stage that simply exists, steady and still. Particles move through it like actors, exchanging their forces. But in gravity, the stage cannot be ignored. The stage bends and flows and curves. It participates fully in the drama. If we try to quantize gravity, we must quantize the stage itself. We must treat space-time as a participant that changes and fluctuates, uncertain and jittery, just like the particles that dance within it. Imagine trying to film a play where the stage twists and shakes unpredictably while the actors are performing. You can no longer separate the story from the structure. Every attempt to simplify becomes a tangle of contradictions. That is where physics stands today with gravity. We can describe planets and stars and galaxies with perfect grace using Einstein's equations. We can describe atoms and electrons with perfect accuracy using quantum mechanics. But at the border between these realms, the mathematics breaks down. Physicists have tried many approaches to repair this divide. One famous attempt is called string theory. Instead of point-like particles, everything is made of tiny vibrating filaments. Different vibrations make different particles, the same way different musical notes come from the same string on an instrument. In that picture, gravity is automatic. It arises from one particular vibration pattern that behaves like the graviton. String theory also smooths out the dangerous infinities by ensuring no particle shrinks to a true point. But string theory demands many extra dimensions of space curled up so tightly we cannot see them. It offers beauty, but not yet direct evidence. Another path is called loop quantum gravity. It imagines that space itself might be woven from tiny loops of quantum geometry, like threads in a cosmic fabric. In this view, the smoothness of space-time is an illusion that only appears when we zoom out. Up close, the universe could be grainy, composed of discrete bits of volume that can never be divided further. Loop quantum gravity avoids some infinities, and it offers testable predictions about the earliest moments after the birth of the universe. But it struggles to explain particles as we know them. Some researchers believe we must abandon both visions and think even more radically. Maybe gravity is not a fundamental force at all. Maybe gravity is an emergent behavior, the way temperature appears when countless molecules move and collide. No single molecule contains temperature. It arises from the collective. Perhaps space-time is the same. No single object creates geometry. Geometry emerges when huge numbers of quantum degrees of freedom become entangled with one another. If that is so, then gravity is not reluctant to be quantum. Gravity is quantum at its deepest level. We simply encounter its classical shadow most of the time because the quantum details are hidden beneath enormous complexity. The fabric of space-time might be a structure built from entanglement itself. That would explain why entanglement does not respect the boundaries of space. Entanglement might be the deeper reality from which space emerges. One day, geometry may be viewed as a consequence of quantum connection, rather than a container for it. To see why such ideas are taken seriously, consider a situation where gravity grows intense and quantum mechanics cannot be ignored, such as the inside of a black hole or the earliest tiny fraction of a second after the beginning of the universe. Einstein's equations predict that space-time curves so sharply that it forms a singularity, a place where distances shrink to nothing and time loses all meaning. But quantum mechanics despises singularities. It demands that uncertainty spread things out. Something must give. Either quantum rules fail, or space-time is forced to change its nature. Most physicists believe that space-time must change. The smooth geometry we know cannot continue forever. At incredibly small scales, it must dissolve into something new. If that transformation is guided by entanglement, then Einstein's grand theory becomes only a low-resolution image of a deeper structure. A map drawn on paper that cannot show the finest details of the terrain. This brings us to a pivotal question. How do we test these ideas in a universe where direct experiments on quantum gravity seem impossible? Black holes are far away. The early universe is locked behind the horizon of time, and the gravitational pull of tiny quantum objects is almost too small to notice. Yet the strength of science lies in its creativity. Researchers have begun to design experiments that may reveal faint hints of quantum gravity here on Earth, using new technologies to push matter to its limit. Before we leap into those possibilities, we need to understand fully why gravity continues to behave, classically even in the presence of quantum matter. A single electron has mass. According to general relativity, even a single electron curves space-time. So why do we not see quantum fluctuations in that curvature? Why does gravity seem to smooth over the jittery uncertainty of particles? One idea is that gravity itself acts as a universal measuring device, collapsing quantum states and forcing objects into classical behavior. Another idea is that gravity remains classical because we have not yet probed the right regime. The truth is still hidden. The universe keeps its deepest architecture tucked away in places we have just begun to explore. But the clues have been placed before us. Entanglement persists across distances. Gravity curves space-time. Time slows in strong gravitational fields. Information can never be destroyed. These facts form a pattern that suggests something profound. Space and time might be built from the way information is shared. As we continue, we will turn our attention toward the smallest scales gravity can touch. We will begin to ask whether individual quantum particles generate gravitational fields that respond to their entangled states. We will explore the possibility that gravity is not just influenced by mass and energy, but by the correlations that bind one object to another in the quantum realm, and we will take one step closer to answering the question at the heart of our journey. Do entangled particles share gravity? Gravity has always appeared as the most classical of all phenomena, the one part of physics that seems safe from the jitter and uncertainty that rule the quantum world. When you drop a stone, there is no wavering about where it will fall. When planets orbit stars, their paths can be predicted across centuries. Gravity seems steady, smooth, and always in control. Yet this appearance may be misleading. The calm surface may hide a restless foundation. Quantum mechanics insists that even emptiness is never truly empty. Space seethes with virtual particles that flicker in and out of existence faster than any clock can tick. If space-time bends under the presence of mass and energy, and if the vacuum contains energy of its own, then quantum fluctuations should produce tiny ripples in the geometry of the universe. But where are those ripples? Why does the world look so stable? The answer may lie in how small these quantum gravitational effects are. Consider a single electron. It has mass, but that mass is so tiny that the curvature it creates in space-time is unimaginably slight. The gravitational field around one electron would be so faint that even the most sensitive instruments humanity has ever built would fail to detect it by a factor so large it almost cannot be expressed. The weakness of gravity hides its quantum face. It allows the classical picture to dominate our everyday world, wrapping quantum truth in a cloak of calm. Yet extreme environments betray hints that the cloak is not perfect. Black holes provide the most dramatic example. When matter collapses under its own gravity, space-time curves violently. According to classical general relativity, the collapse continues without limit until all the mass is squeezed into a single point of infinite density. But quantum theory would never allow such a point. There must be a lower bound, a smallest grain of space-time. Something prevents the final step into infinity. Otherwise, the laws of physics would cease to apply. Stephen Hawking discovered another clue. Black holes are not perfectly black. They emit a faint glow of radiation due to quantum effects near the event horizon. This radiation slowly drains energy from the black hole, causing it to shrink and eventually vanish. But if it vanishes entirely, what happens to the information that fell inside? Quantum mechanics states with unyielding certainty that information can never be destroyed. Gravity seems to disagree. This conflict is called the black hole information paradox, and it forces us to confront the quantum nature of space-time, whether we are ready or not. Time itself becomes suspect under the scrutiny of these ideas. Einstein showed that clocks tick more slowly in a strong gravitational field. Time is not universal, but quantum theory relies on time as an external parameter, a backdrop against which probabilities evolve. If time can curve, stretch, and twist, then how do we write quantum rules for the universe as a whole? Where do we place the observer when the observer is part of the very geometry in question? The two great theories argue not only about reality, but about the framework within which reality is described. Perhaps the difficulty arises because we are trying to force nature into categories that make sense only at certain scales. The smooth geometry Einstein revealed is a large-scale phenomenon. It describes many particles acting together. But when we look closely at a fluid that seems smooth, we find molecules dancing unpredictably. When we feel the warmth of sunlight, we are really feeling countless photons striking us. Maybe geometry, too, is built from tiny fundamental ingredients. Those ingredients might be qubits of information. They might be relationships of entanglement. They might be something we have not yet imagined. There is a powerful thought experiment that captures the essence of this challenge. Imagine holding two particles close together so that their quantum wave functions overlap. According to general relativity, their masses generate gravitational fields that blend smoothly. But according to quantum mechanics, their states can be superpositions. They can be in multiple places at once. If the particles are placed into a superposition of being near and far apart, then the gravitational field must also enter a superposition. Gravity would need to be quantum. Otherwise, something would break. Either the particle superposition collapses, or the gravitational field must carry its own uncertainty. The universe cannot hold to classical rules and quantum rules at the same time in such a situation without contradiction. This argument hints that gravity must ultimately be quantum. It cannot remain the one classical rebel in a quantum universe. And if gravity is quantum, then perhaps entanglement plays a central role. When two particles become entangled, their joint state describes not only their spins or energies, but also how they curve spacetime around them. If their quantum link has gravitational consequences, then the curvature created by one particle could be influenced by the other even at a distance, not as a signal, not as a violation of causality, but as a shared structure in the geometry that connects them. We stand before a question that could reshape physics. Does entanglement produce gravitational correlation? When one particle falls into a superposition of being here and there, does space-time also fall into a superposition? And if two particles share a quantum bond, does gravity treat them as one system rather than two separate masses? If the answer is yes, then the boundary between quantum mechanics and gravity dissolves. The two stories merge into a single narrative. The challenge now is to find a way to observe such tiny effects, to probe the universe at a scale where the quantum grain of gravity reveals itself. Recently, scientists have begun to design experiments that may detect gravitational entanglement between small masses. If such entanglement appears, it would mean that gravity can act as a carrier of quantum information, even if it cannot send messages faster than light. It would be the first true evidence that space-time is woven from quantum threads. Our journey is moving closer to that frontier. In the chapters ahead, we will see how researchers plan to test the quantum nature of gravity. We will explore satellites that send entangled photons across continents. We will examine proposals that treat wormholes not as science fiction, but as mathematical reflections of entanglement. And we will push toward a possible unification of the largest scales and the smallest. Gravity has been the oldest known phenomenon in physics. It might turn out to be the newest discovery all over again. The reluctant quantum, hiding in plain sight, waiting for us to notice the subtle trembling of space-time beneath our feet. Every object with mass or energy shapes the geometry around it. That is the central claim of general relativity. It applies not only to stars or planets or apples falling from trees, but also to the smallest pieces of matter the universe allows. Even a lone electron curves space-time. The effect is unimaginably tiny, far too subtle for any modern instrument to detect, but the mathematics leaves no way around it. Mass means gravity. Energy means gravity, and quantum particles carry both. This leads to a strange contradiction in how we think about the world. Quantum mechanics teaches that particles are not tiny marbles. They exist as clouds of probability. An electron can be in more than one place at the same time until a measurement collapses its wave function. If the electron is in a superposition, then where is its gravitational pull? Does it curve space-time in two places at once? Does space-time itself become uncertain? For now, the honest answer is yes. If a particle can be in different positions, then the geometry must reflect that possibility. But because gravity is so weak for such tiny masses, the uncertainty in curvature is incredibly small. It slips beneath the threshold of everything we can detect. The quantum nature of space-time hides inside the noise of everyday existence. This is not a failure of theory. It is a limit of our technology. We are trying to find ripples on a pond that is almost perfectly still. But the ripples must be there, trembling at scales our senses cannot reach. To understand why scientists believe this so strongly, recall the most famous equation in physics. Energy equals mass multiplied by the speed of light squared. In words, energy and mass are two faces of the same physical quantity. A photon of light carries energy and therefore gravity. A beam of light can bend space-time, and in return space-time can bend the path of light. This has been observed many times, even in the way stars appear slightly shifted from their true positions when their light passes near the sun. If light, which has no rest mass, can produce gravity through its energy, then the quantum nature of light must affect gravity. And if electrons or quarks or entire atoms can exist in superpositions, then the gravitational field they produce must also be placed in a superposition. Geometry cannot remain classical while matter becomes quantum. Yet in most situations, quantum gravitational effects average out. The number of particles involved in a typical object is so immense that their individual uncertainties wash away. A grain of sand contains more atoms than all the stars visible to the naked eye in the night sky. Their collective gravitational influence smooths into a classical field so steady that planets follow perfect ellipses around the sun year after year. The quantum jitters of spacetime are drowned beneath overwhelming numbers. But when the numbers shrink, when we focus on one mass or two masses, everything changes. The rules of quantum mechanics return with full authority. If we cool a tiny object so much that its motion slows to nearly absolute stillness, we can cause its center to enter a quantum state. If we then isolate that object from vibrations, from heat, from stray photons of light, we can protect its superposition long enough to measure its gravitational effect. This is the frontier of modern physics. Researchers are building devices that hover on the edge between classical certainty and quantum strangeness. They trap small spheres of matter inside electromagnetic fields. They chill them to temperatures near absolute zero. They eliminate every whisper of outside influence. And then they try to see whether gravity responds to the strange rules of quantum superposition. One famous proposal suggests splitting a tiny mass into two possible positions at the same time. If its gravitational field also splits, then another nearby mass should feel two different gravitational pulls simultaneously. That second mass would then become entangled with the first purely through gravity. Such a result would demonstrate that gravity can carry quantum information. It would prove that spacetime is not only curved, it is quantized. To reach that moment, we must first understand something subtle. Gravity does not behave like a traditional force in the quantum world. The gravitational field cannot simply be treated as a particle exchange between two masses. The curvature of spacetime tells matter how to move, but the curvature itself must follow quantum uncertainties if matter does. It is not clear whether this quantum curvature exists everywhere, or whether it emerges only in specific situations where quantum correlations demand a shared geometry. Even the question of location becomes different. If two quantum particles are entangled, they share one wave function. In that case, their gravitational influence may not arise independently. Instead, the gravitational field might reflect their joint state, a single curve in the fabric of spacetime that knows the connection between them. Picture two particles bound by entanglement. They drift apart. Space stretches between them. Yet quantum mechanics insists they are still one system. Gravity insists that mass shapes the space between objects. If entanglement keeps their identities knitted together, perhaps spacetime bends along the thread that ties them. Perhaps the gravitational field cannot fully separate what quantum mechanics keeps united. This idea is more than poetry. It has mathematical consequences. If gravity can respond to quantum entanglement, then the strength of gravitational attraction may depend slightly on the degree of entanglement between objects. Not enough to change everyday life, but enough to reveal that the classical picture is only the large-scale limit of a deeper quantum truth. We must be cautious. These ideas are not proven. They stand at the edge of knowledge, but they are testable. Experiments are being built. And the results could reveal whether the link between mass and geometry stretches into the quantum realm. The next step in our journey will involve gravity meeting entanglement directly. We will explore how curved spacetime can influence quantum connections, slowing clocks, and stretching waves. We will see how entanglement persists in orbit around Earth, and perhaps even near black hole horizons. Then we will turn the question around and ask whether entanglement can influence gravity in return. we are beginning to glimpse the unity behind the universe. Matter, energy, information, geometry, all might be woven together in one fabric beneath the visible world. When we look closely at a single particle, it does not sit still the way our everyday intuition expects. An electron, or an atom, behaves like a probability cloud that spreads through space. The cloud describes all the places the particle could be found if someone were to measure it. Until that moment, the particle is not located anywhere specific. It is suspended between realities, existing as a possibility of being here and a possibility of being there. This superposition is one of the most profound features of quantum theory. It treats the world not as a set of definite positions, but as a web of potential outcomes waiting to become real. Now imagine that same particle as a tiny source of gravity. In classical relativity, a mass curves spacetime around a particular point, but in quantum mechanics, there is no particular point. The particle does not choose a location until forced to do so. Therefore, the curvature it creates must also be spread out. The gravitational influence becomes a superposition of shapes. Spacetime, at the smallest scale, might be more flexible and uncertain than we ever imagined. The very geometry that holds the universe together could ripple with probabilities. Some scientists think this uncertainty remains hidden because gravity forces quantum particles to collapse into definite states. The idea suggests that superpositions cannot survive once they become heavy enough. Gravity would turn quantum clouds into classical objects by pulling them into a single location. If this is true, then gravity plays a role in shaping reality itself, choosing which potential futures become actual events. But others argue the opposite. They believe gravity honors quantum rules completely, allowing even geometry to enter a superposition. In that case, gravity becomes part of the quantum story, not the destroyer of it. To decide between these possibilities, experimentalists need to push technology to its absolute limits. They work with masses that are almost too small to see. Tiny spheres of metal or crystals made from thousands of atoms are cooled until their motion nearly stops. Lasers isolate them from vibrations. Magnetic fields cradle them in perfect balance. The goal is to prepare these objects so delicately that their entire form behaves like a single quantum particle. The object can then enter a superposition of being in different places at the same time. If gravity responds differently in each location, we should be able to detect a faint signature of that difference. But even if we succeed in placing one object into a gravitational superposition, detecting the effect requires another clever idea. Quantum mechanics tells us that measurement should reveal a paradox only when two systems interact. So researchers bring a second tiny mass near the first. If the gravitational influence of the first mass exists in two positions, then the second mass will feel two forces at once. The result would be that the two masses become entangled by gravity alone. Their fates would intertwine without any other force connecting them. If scientists observe such entanglement, it will mean that gravity itself can transmit quantum correlations. This is the dream of several pioneering proposals. They describe arrangements where two small spheres hover only a few micrometers apart. Each sphere is prepared in a superposition. If gravity is truly quantum, the spheres should share entanglement. If gravity remains classical, the entanglement will never appear. The outcome would reveal whether spacetime can truly participate in quantum information flow. Supporting this effort are insights from the behavior of atomic clocks placed at different heights on Earth. Time flows faster for clocks farther from the ground because gravity weakens with distance from Earth's center. This means that quantum phases evolve differently depending on gravitational position. When atoms become entangled, any difference in the flow of time can twist their quantum connection. Entanglement becomes sensitive to curvature. It can be stretched or weakened by the geometry of spacetime. That effect is tiny, but it has already been measured with remarkable precision. Experiments with satellites have carried entangled photons high above Earth, separating them by hundreds of kilometers. The entanglement survived the journey. proving that the bond can withstand the shifting flow of time in a gravitational field. Gravity influences entanglement, but does not break it easily. This tells us that entanglement is not fragile fluff. It is a structural feature of the universe, able to endure even as the geometry around it changes. And still, the most enticing idea waits just ahead. If gravity can affect entanglement, then entanglement may affect gravity. The relationship might work in both directions. If the presence of mass curves spacetime, and if the quantum state of that mass determines how that curvature appears, then information about entanglement would be written into the geometry itself. It would mean that gravitational fields do not merely describe where objects are, they describe how deeply objects are connected in the quantum sense. Consider two particles that were once united, created from a single event. They travel apart as separate objects, but entanglement keeps them tied in ways that do not require physical contact. In classical physics, they would drift apart, and their gravitational fields would weaken with distance. But if entanglement influences geometry, then a faint thread of curvature might persist between them, not strong enough to pull them back together, not strong enough to violate the speed of light, but present nonetheless, a hidden line etched into spacetime by quantum unity. Such a thread would reveal a new property of gravity. It would show that the shape of space does not depend solely on matter and energy, but also on the invisible bookkeeping that quantum mechanics performs. Even when objects are separated by oceans of emptiness, the universe may remember that they were once one. That memory could be what gravity reads when it shapes the path of particles. This is a radical vision, and we must test it with clear eyes. Bold imagination must be matched by bold experimentation. The technology is advancing rapidly. The amount of entanglement generated by gravitational interaction would be tiny, but not impossible to measure. If the effect shows up, it will mark a turning point in the history of science. It will mean that gravity has joined the quantum family at last. We have traced the influence of particles on the curvature of spacetime. We have seen how superposition challenges the classical picture of gravity. We have imagined the first experiments that might reveal gravitational entanglement. Now it is time to explore how the geometry of the universe, in turn, shapes quantum connections across vast distances. For entanglement does not only reach through space, it must pass through spacetime itself, bending and twisting as gravity commands. Entanglement does not float in a vacuum untouched by the world around it. The universe is never perfectly still. Spacetime curves wherever mass and energy exist, and that curvature influences how time flows. Quantum states evolve as time passes, so anything that changes the passage of time can change the evolution of entanglement. This is one of the most subtle and profound lessons physics has uncovered. Quantum mechanics and gravity are not strangers. They are constantly interacting even in the quiet everyday places where we live. Imagine two photons created in an entangled state and sent along different paths. One climbs upward against Earth's gravitational pull. The other travels horizontally. Because gravity slows time near Earth's surface, the photon that remains lower experiences time passing just slightly more slowly. The quantum phase that governs its behavior changes at a slightly different rate than the phase of the photon that climbs higher. Even the tiniest difference builds over distance. When the photons are compared again, scientists find that gravity has altered their entanglement, not destroyed it, but twisted it. The geometry of space-time has left its signature on the quantum link. This phenomenon has already been measured. Experiments using satellites have demonstrated that entanglement can survive separations of hundreds of kilometers. The famous quantum science satellite named Meteus, launched by researchers in China, sent entangled photons from orbit to two distant ground stations. Despite the curvature of spacetime and the changing flow of time along the journey, the entanglement endured. The universe proved again that quantum unity is stronger than distance, and stronger even than gravity's attempt to stretch and slow the flow of time. Yet there are places where gravity is far more powerful than anything we experience on Earth. Near a black hole, space-time curves into a steep well. Time slows so dramatically that a distant observer would see a clock near the event horizon almost freeze. In such places, entanglement faces a harsher trial. If one member of an entangled pair falls toward a black hole while the other escapes, the gap in their experience of time becomes enormous. Quantum theory predicts that the entanglement should degrade. Some studies suggest that information about the falling particle becomes encoded in the horizon itself, smeared across the surface like a hologram. Others argue that the entanglement might survive in a transformed state, hidden behind the horizon in ways we cannot yet decipher. This forms part of the black hole information paradox. It is not only a question about what happens to objects that fall inside. It is a question about what happens to their quantum relationships. If entanglement is destroyed, then information vanishes. If information vanishes, quantum mechanics breaks. The universe appears unwilling to allow that. Every path we follow suggests that information must remain in the world somehow, even if it becomes tangled into the geometry where we cannot easily read it. Gravity and quantum mechanics clash, but the structure of reality refuses to let either one emerge as the sole winner. These examples reveal something crucial. Gravity interacts with quantum connections continuously. Entanglement feels the shape of space-time. It stretches when space-time stretches. It twists when time flows at different speeds. It weakens when geometry becomes extreme. Entanglement is not separate from the universe. It is woven into it. This brings us to the heart of our investigation. If gravity can influence entanglement, even subtly, then perhaps entanglement can influence gravity. The feedback could work in both directions. Each thread might tighten the other. The curved stage and the quantum actors might not be separate at all. They might be one structure viewed through two different ideas. There are whispers of this relationship in mathematical discoveries linking quantum information and space. Some ideas propose that the amount of entanglement inside a region determines the amount of space that region can hold. If the entanglement drops to nothing, the space could collapse. This turns the question of geometry from a physical problem into a problem about information. It implies that the smoothness of spacetime seen in general relativity emerges from a deeper network of quantum links. If these ideas prove correct, then the curvature created by mass would not only depend on energy and density, it would depend on whether the particles are entangled. Entanglement could become a quiet architect of geometry, influencing how space shapes itself around quantum matter. That is why the frontier experiments are so important. If scientists observe gravitationally mediated entanglement between tiny masses, it will confirm that gravity responds not only to where matter is, but also to how matter is connected. It will suggest that the quantum state of the universe does not merely live within space-time, it builds space-time. We are still far from solving the puzzle, but every clue takes us closer. Entangled photons orbit Earth and return still bonded. Entangled atoms experience time differently depending on height. Quantum information appears to survive even the deadly interior of a black hole. All these threads point in the same direction. Quantum mechanics and gravity are not enemies. They are puzzle pieces that fit together in a new and unexpected way. Our next step is to explore how entanglement behaves in curved space-time from a more detailed perspective. We will examine the role of gravitational time dilation on quantum coherence. We will follow entangled systems on journeys through different gravitational potentials, and we will deepen our understanding of how gravity influences the evolution of the quantum world. As this investigation progresses, the original question becomes richer and more urgent. Do entangled particles share gravity? The universe seems to hint yes in a quiet whisper carried through every experiment. But hints are not answers. The truth waits for us in the experiments yet to be completed. Gravity does not only shape the motion of planets and falling stones, it shapes the flow of time itself. Near a massive object, moments stretch. Clocks tick more slowly. A person standing on a high mountain ages a little faster than someone at sea level, because the strength of gravity is slightly weaker up high. The difference is small, but it is real and measured. Time is not uniform across the universe. It bends and curves with space-time. And because quantum states evolve as time passes, entanglement must be influenced wherever gravity slows or accelerates the rhythm of reality. Imagine two atoms prepared in a beautiful entangled state. Their internal clocks begin ticking the moment we set them free. One atom is placed deep underground where gravity is stronger. The other rises to a satellite in orbit above Earth, where gravity is weaker. Days later, when we bring them back together, we discover that their clocks have not ticked at the same speed. Their quantum phases have drifted apart. The entanglement has been twisted by the difference in how time flowed along their separate journeys. Even though space-time did not break their bond, it left fingerprints on the connection. This phenomenon has been demonstrated with astonishing precision. Scientists have separated entangled photons and sent them along different paths. One stayed close to the ground, while the other climbed high in a rocket or on a satellite. When the photons were reunited, their entanglement still existed, but altered. Gravity had not destroyed the correlation, but it had changed the story they shared. Entanglement is sensitive to the geometry of time. The satellite experiment known as MISSIOUS revealed just how far quantum links can stretch. Photons were created together and then sent down to distant ground stations separated by more than 1,000 kilometers. Even while passing through the ever-shifting curvature of space-time and the changing flow of time along their paths, the entanglement endured. It survived the journey from orbit to Earth through miles of air, turbulence, and the constant pull of gravity. The universe seems determined to keep entanglement alive. But what happens when gravity becomes extreme? Near a black hole, time slows drastically. If one particle from an entangled pair falls toward a black hole while the other escapes into open space, their experiences of time diverge beyond anything Earth can provide. The falling particle appears to freeze from the perspective of the distant observer. The one that escapes continues evolving normally. In this situation, quantum theory predicts that the entanglement will suffer. The bond frays as the difference in time flow grows unbearable. Yet even here, nature refuses simple answers. Physicists believe that information about the falling particle may become imprinted on the event horizon of the black hole. The horizon could act like a cosmic memory surface, recording the quantum details of everything that approaches. Entanglement might persist, not as a direct link between the two particles anymore, but through a complex structure involving the horizon itself. Some theories propose that the entanglement is not destroyed, but redistributed, hidden inside the geometry in ways we cannot observe directly. That would protect the sacred rule of quantum mechanics that information can never fully vanish. This struggle between time dilation and entanglement appears in more subtle places too. In a room where the gravitational field changes slightly from floor to ceiling, time already flows at different rates. If we place an entangled system across that small distance, the entanglement will gradually degrade. Not immediately, not dramatically, but gently, as if gravity is a constant whisper urging the quantum bond to unravel. This effect is small enough that only the most precise experiments can detect it. Yet it confirms again that spacetime and entanglement are inseparable parts of one reality. Even light itself feels the influence of gravity on entanglement. When photons travel near a massive body, their paths bend ever so slightly. Their quantum phases shift. Entangled beams of light do not merely move through space. They move through geometry shaped by the mass of everything around them. As the geometry bends, the entanglement bends with it. Quantum information flows along the contours of spacetime like a ribbon weaving through invisible hills and valleys. Scientists are starting to use these effects as tools. Entangled systems placed in different gravitational potentials can act as probes of curvature. They can detect minute differences in the flow of time to levels impossible for classical devices. A new field is emerging at this intersection of quantum sensing and gravitational physics. It suggests that entanglement may become one of our best instruments for exploring the shape of the universe. All these discoveries show that gravity shapes quantum links. But the effects described so far belong to gravity acting on entanglement, not the other way around. They show that curved spacetime influences the evolution of quantum systems as they move through it. They do not show that quantum systems influence the shape of spacetime through their entanglement. For now, the connection seems one-sided. Yet there are hints of symmetry. If entanglement can be twisted by spacetime, then perhaps spacetime can also be twisted by entanglement. If geometry marks the flow of information in the universe, then the deepest connections between particles might leave faint marks in the curvature. These marks would not change the grand orbits of planets or the fall of stones. They would be too small for ordinary life to notice, but in the delicate world of experiments with small masses, they might be detectable. This possibility changes the way we think. We no longer ask merely whether gravity affects entanglement. We begin to ask whether entanglement might be a source of gravity. If two particles remain united by a quantum bond, even across vast distances, perhaps spacetime keeps track of that unity in a subtle way. The gravitational field might encode not only location and mass, but also connection. The stage is set for a leap into deeper speculation, supported by emerging evidence. In the next part of this chapter, we will explore theories that push us toward a radical possibility. Entangled particles may not simply share information, they may share geometry. The link between them might be more than statistical correlation. It could be a tiny worm-like tunnel through the structure of spacetime itself, a bridge beyond distance, a new understanding of unity. When we ask how entanglement behaves in the presence of gravity, we are really asking how the universe keeps its promises. Quantum mechanics promises that information is never lost. General relativity promises that spacetime bends exactly as mass and energy demand. These promises sometimes appear to clash, especially around black holes, where time slows to near stillness and the future becomes sealed behind a horizon, from which even light cannot escape. But the universe has not broken its word yet. Each principle continues to hold true in every test we can perform. This suggests that the conflict does not lie in nature, but in our current understanding. For years, researchers assumed that entanglement would unravel when stretched too far by gravity. They imagined that the horizon of a black hole would tear quantum bonds apart. But new ideas propose a more elegant answer. Instead of letting entanglement die, the geometry of spacetime may reshape it. The information from the falling particle could become encoded in the horizon itself in a quantum pattern. The black hole might not swallow entanglement, but transform it into a new form that keeps the promise of information conservation alive. This shift in thinking introduces the idea that geometry and entanglement might be two sides of the same coin. Where there is entanglement, there is structure. Where structure appears, geometry forms. Curvature might emerge from patterns of connection. This idea gains support from studies of quantum fields in curved spacetime. In empty regions of the universe far from stars or galaxies, vacuum energy still exists. Quantum fluctuations ripple through what seems like emptiness. These fluctuations are not random chaos. They are tied together by entanglement across space. The vacuum itself forms a lattice of quiet communication, linking every region to every other. Without these links, empty space would not behave as it does. Put differently, spacetime without entanglement might cease to be spacetime. What we call distance, what we call shape, may arise from the strength and structure of the quantum links that tie tiny pieces of the universe together. Entanglement could be the invisible scaffolding that holds the cosmos upright. There are experiments that hint at this connection, even if indirectly. When scientists separate entangled particles across long distances, the quantum bond persists regardless of the journey through Earth's gravitational well or through the cold emptiness of orbit. This implies that entanglement is not something that must be preserved by pushing against gravity. Instead, gravity and entanglement negotiate constantly, keeping a mutual account of time flow and separation. Light traveling through curved spacetime shows this most clearly. As a photon dips into a stronger gravitational region and time slows, its quantum phase advances at a different rate than a twin photon traveling a different route. When the two are compared again, their shared entanglement carries the story of their journey. Entanglement becomes a journal of how spacetime treats information. In the deepest regions of a black hole, theory stretches and trembles. If two particles are entangled and one crosses the horizon, quantum mechanics says the bond should persist. If the horizon ends the bond, then information is lost. The universe seems unwilling to allow this. Some theories propose that the horizon grows a structure called a firewall, which burns away entanglement. Others propose that the horizon is not a wall, but a bridge, where quantum information becomes woven into the geometry. In this picture, entanglement does not break. It changes shape. The gravitational boundary becomes a surface of stored information. When viewed through this lens, gravity begins to look more like a consequence of entanglement than a cause of its destruction. The curvature of spacetime is the result of quantum relationships that cannot be ignored. The geometry of the universe might know which particles are connected and reflect that knowledge in the shape of space. This possibility pushes us toward a radical question. Could the gravitational attraction between objects arise because entanglement binds their quantum information together? Could the pull we feel toward Earth be the macroscopic shadow of countless microscopic entanglements, forming and reforming inside matter? If entanglement increased, would gravity grow? If entanglement vanished, would geometry collapse into points without dimension? These ideas are daring, but they are grounded in mathematics that continues to grow stronger each year. Researchers have discovered deep relationships between the amount of entanglement in a region and the volume of spacetime that region occupies. Remove entanglement beyond a certain threshold, and the geometry might tear apart. That tearing is not hypothetical. It appears in certain theoretical models where spacetime ceases to exist if quantum correlations disappear. We have crossed from describing entanglement in curved spacetime to imagining curved spacetime produced by entanglement. The relationship between quantum mechanics and gravity has turned in on itself. The effect and the cause may be trading places, but imagination alone cannot decide the truth. The next step demands evidence. We must build experiments that expose the quantum nature of gravity. The final part of this chapter will follow that quest. Scientists around the world are preparing to test whether gravity can transmit entanglement between small masses. If this experiment succeeds, it will prove that gravity is a quantum phenomenon. It will show that spacetime carries information about quantum relationships. And it will mean that entangled particles do not simply share correlations. They may share gravity itself through a geometry that recognizes their connection. Entanglement has already shown that our assumptions about the nature of distance are flawed. Two particles can be separated by great spans of space and yet behave as if they remain part of a single object. Gravity has shown that our assumptions about the nature of time are flawed. Two clocks can tick at different speeds simply because of where they rest in a gravitational field. When these two mysteries meet, we begin to see a new picture emerging, one where connection and curvature are tied together at the most fundamental level. Time dilation is not just an inconvenience for entangled systems. It is a tool that reveals the shallowness of our classical view of space. It tells us that the flow of time depends on gravitational potential. Entangled particles moving through regions of different curvature evolve differently, and their entanglement carries the imprint of that difference. Every twist in their shared quantum state is a message written in the geometry of spacetime. One might wonder if we could someday use entanglement to map gravity with unprecedented detail. The answer is yes, and early steps have already been taken. Scientists use entangled atoms as sensors that can detect slight changes in gravitational pull with astonishing accuracy. These quantum pairs become delicate probes of curvature. They can reveal tiny variations in the shape of Earth that classical instruments would completely miss. The same approach may one day help us detect underground voids, measure changes in water levels deep below the surface, or even monitor the movement of tectonic plates before earthquakes strike. This practical progress comes from the same fundamental interaction that lies at the heart of our exploration. Gravity influences entanglement, but the more we learn, the harder it becomes to believe that this influence travels in only one direction. If the curvature of spacetime changes the structure of entanglement, then the structure of entanglement might change the curvature of spacetime in return. The relationship may be symmetric, a mutual conversation between geometry and quantum information. To imagine how this could work, picture entanglement as a web connecting pieces of matter. The stronger the web, the more those pieces behave as one. If spacetime is built from those webs, then gravity emerges from the tension in the network. Where quantum information is densely linked, spacetime expands. Where entanglement weakens, spacetime thins. If the links vanish entirely, space could collapse or disconnect. Imagine a bridge held up not by stone, but by the trust between two travelers. If the trust dissolves, the path collapses into emptiness. This vision suggests a strange new way of thinking about black holes. They may not be monsters that destroy information, but engines that transform it. The event horizon could be an information surface, where quantum details about what falls inside become entangled with the geometry itself. The interior of a black hole could be a dense network of quantum links, so compressed that spacetime nearly tears. Entanglement becomes the force that holds the collapse together, refusing to let information die, even when matter vanishes from view. One of the most intriguing possibilities is that entangled particles might be connected by something like a tiny worm-like shortcut in spacetime. The idea is not that signals travel through it. The shortcut would be so tight and so twisted that nothing could pass through. But the connection could exist. Mathematically, reflecting the structure of the entanglement, distance would lose its power inside this hidden geometry. What we call far could be near in ways we cannot picture easily. As experiments push forward, the focus sharpens on small systems. If gravity can generate entanglement between objects too tiny to influence each other in any classical way, it will prove that gravity is quantum. It will reveal that the curvature of spacetime contains quantum uncertainty. It will show that geometry responds not only to the presence of mass, but to its quantum state. This is not idle hope. Scientists have already proposed realistic designs for such experiments. In carefully controlled chambers, tiny spheres will be placed in delicate balance. They will be cooled until they behave as quantum objects. Then their gravitational interaction will have a chance to entangle them. If that entanglement appears, gravity will have spoken its first clear quantum word. And yet, even if we detect gravitational entanglement here on Earth, the implications reach far beyond our planet. They stretch into the heart of the cosmos. They touch the birth of the universe itself. The earliest moments after the beginning of time were ruled by quantum fluctuations in a sea of energy so dense that space-time vibrated wildly. The structure of the universe today may still carry the imprint of those early quantum connections. If entanglement shapes curvature, then the galaxies scattered across the cosmos, the filaments of dark matter stretching through the void, the clusters of stars swirling in grand formation, all may be the result of ancient quantum bonds that gave space-time its first form. The geometry of everything we see might be a fossil record of entanglement that existed long before atoms formed. We stand on the threshold of a profound idea. Entanglement does not merely exist within space-time. It helps create space-time. Gravity does not destroy quantum connections. It depends on them. The bending of light, the slowing of time, the fall of objects, may all be emergent features of a deeper order that unites information with geometry. In the next chapter, we will step fully into this daring vision. We will examine one of the boldest proposals in modern theoretical physics. It claims that entanglement and geometry are not just connected, but are actually the same thing seen from different perspectives. If this idea is right, then when two particles become entangled, their connection is not through invisible magic. It is through a hidden bridge in the structure of space-time itself. The universe has always challenged our imagination, but sometimes it offers a path forward at the very moment when confusion seems impossible to escape. Gravity and quantum mechanics have argued silently for more than 100 years. Each describes a different side of reality with astonishing success, yet they refuse to meet peacefully in the middle. Then, in the second decade of the 21st century, two physicists made a proposal that surprised the world. It suggested that perhaps the two great theories of the universe are not separate at all. They may be two ways of describing the same thing, and the secret that connects them could be entanglement itself. This bold idea was introduced by Juan Maldacena and Leonard Susskind. They asked us to imagine that when two particles become entangled, something happens in the geometry of space-time. The particles are no longer isolated objects floating in emptiness. They remain connected through a hidden structure, and that structure looks like a wormhole. Not a wormhole that one could ever travel through, not a tunnel for sending messages, but a subtle and sealed bridge in the invisible fabric of space-time. To understand why this idea matters, we must step back and recall the two puzzles that once seemed unrelated. The first puzzle, called EPR, was raised by Albert Einstein, Boris Podolsky, and Nathan Rosen. They argued that quantum mechanics must be incomplete because it allowed what Einstein called spooky action at a distance. Two entangled particles can be separated by vast distances and yet behave as though they share the same mind. Einstein found this disturbing. He believed no influence should travel faster than light. If quantum mechanics allowed such instant links, something deeper must be going on. The second puzzle also came from Einstein and Rosen, but at a completely different time and from a completely different idea. They imagined that general relativity allowed bridges in space-time that could connect distant regions. These bridges were named Einstein-Rosen bridges and are known today as wormholes. They are curious creatures of geometry. They may be possible according to the mathematics, yet they cannot remain open without collapsing instantly. They seem like doors that lead nowhere, forming and disappearing without allowing anything to pass through. For decades, these two ideas lived in different corners of physics. One was about quantum strangeness, the other was about geometry. No one imagined they could be two descriptions of the same phenomenon, but Maldacena and Susskind proposed exactly that. They suggested that every time two particles are entangled, an invisible and non-traversable wormhole appears connecting them. The wormhole does not allow signals. It does not violate the speed of light. It does not let us cheat causality. It simply expresses the unity of the entangled state in a geometric language. Entanglement and wormholes become linked. The EPR correlations become identical to ER geometry. Two phenomena become one truth. Therefore, the name of the idea is ER equals EPR. Entanglement equals geometry. Connection equals curvature. This is not wild speculation. It builds upon discoveries in a field called ADS-CFT correspondence, where a quantum theory without gravity can be equivalent to a gravitational theory inside a curved space-time. In these studies, the amount of entanglement among quantum particles determines how much space exists in the gravitational picture. If the entanglement changes, the space-time geometry changes. Remove entanglement entirely, and space itself collapses. It is as though geometry is not a stage, but a woven cloth, and the threads that hold it together are quantum correlations. The ER equals EPR proposal pushes this idea further. It whispers that gravity and quantum mechanics are not enemies. The apparent conflict is simply a mismatch between languages. Quantum mechanics speaks with probability and entanglement. General relativity speaks with curvature and geometry. ER equals EPR says these two languages tell the same story. They describe different aspects of a single underlying reality. This changes how we view even the most terrifying objects in the cosmos. Black holes were once believed to swallow information forever. Matter falls inward, light cannot escape, everything disappears. But quantum mechanics insists that information can never be destroyed. The universe must preserve every detail, no matter how deeply it hides it. This conflict led to the famous black hole information paradox. It is one of the greatest challenges in all of physics. If ER equals EPR is correct, then the paradox softens. When something falls into a black hole, it becomes entangled with the interior. That entanglement might be represented by wormholes. The connections between the inside and the outside remain. Information is not destroyed, but stored within the geometry. The event horizon becomes a surface rich with quantum detail. Every particle that falls in leaves its mark. The black hole is not a tomb of information. It is a vault. As the black hole slowly evaporates through Hawking radiation, the information may leak back out, not as the original objects we recognize, but as quantum correlations encoded in the radiation. The entanglement becomes the escape route for knowledge. Nothing travels faster than light. No rule of physics is broken. The wormholes remain sealed. But the unity of the quantum state ensures that information remains alive. This vision is breathtaking. It hints that the universe is not built from objects but from relationships. Entanglement becomes the foundation. Geometry becomes the consequence. Even space itself may exist only because countless particles remain entangled with one another. Remove the entanglement and the structure falls apart. In this picture, the entire cosmos is a network of quantum bonds. Every star, every planet, every particle in your body is part of a gigantic tapestry of entanglement. Gravity may be the large-scale expression of this network. The curvature of space would then be the shadow of quantum unity. One might imagine that the space between Earth and the Sun is empty, but perhaps it is filled with quantum threads that preserve the structure of distance itself. These threads are not matter, they are not energy. They are entanglement, quiet and unseen. They give reality its shape. The ER equals EPR hypothesis transforms the way we think of separation. Two objects that appear far apart in ordinary space might be close in the hidden geometry of entanglement. Distance becomes a matter of perspective. When we say two particles are entangled, we may really be saying that in the deepest fabric of spacetime, they are neighbors touching through a secret connection. This view leads to many questions. If entanglement creates geometry, what creates entanglement? How did the universe become connected in the first place? Does the expansion of space reflect a strengthening of these connections or a stretching of them? Could dark energy and dark matter hint at entanglement we do not yet understand? And what about the future of the universe? If entanglement gradually decays in certain regions, will those regions eventually lose their geometry? Could space itself dissolve into a fragmented patchwork of isolated islands? These mysteries are not yet answered, but the idea that entanglement and geometry are deeply related has already reshaped theoretical physics. It gives researchers a new way to explore the boundary between the quantum and the gravitational. It offers hope for unification not through force, but through connection. Not through domination, but through cooperation. The universe appears to be one thing, not two. Perhaps the greatest lesson of ER equals EPR is that the universe knows how to remain whole even when it appears divided. Entanglement laughs at distance. Wormholes bend the meaning of separation. Gravity weaves everything into one continuous geometry. And quantum mechanics insists that every event influences the structure of reality. We are not separate from the cosmos. We are part of its living structure. Our atoms are connected to distant matter through ancient threads of entanglement. Our very presence curves spacetime. We walk across a floor built from relationships millions of years older than Earth itself. The implications of this remain beyond full comprehension, but the idea shines like a beacon guiding us through darkness. It suggests that the truth of the universe is unity. A unity so profound that what looks like empty space is actually full of connections. A unity so fundamental that even light obeys its structure. A unity so intricate that entanglement might be the fabric from which gravity is woven. If ER equals EPR is correct, then every entangled pair is a tiny experiment in quantum gravity. Every quantum connection is a thread in the architecture of space-time. And every scientific discovery that deepens our understanding of entanglement also deepens our understanding of gravity. The two are not different mysteries, but one. The next chapter will bring us closer to experiment, where imagination and mathematics must finally meet reality. We will explore whether tiny objects in laboratories on Earth might reveal the quantum nature of gravity. We will examine proposals that aim to catch gravity in the act of creating entanglement itself. If this succeeds, it will mean the universe has whispered its secret to us at last. Gravity shares the quantum soul of everything else. Every scientific revolution begins as a question. Some questions feel so deep that they echo across centuries. What is gravity? What is quantum reality? For a long time, these questions traveled parallel roads. Gravity ruled the cosmos with gentle curves of space and time. Quantum mechanics ruled the microscopic world with possibilities and probabilities. Each appeared complete within its own domain. But the universe is not divided between large and small. It is one seamless whole. And so the two questions have finally collided into one. Does gravity itself arise from quantum entanglement? Can the invisible bonds between particles shape the structure of space around them? To explore this, scientists are designing some of the most delicate experiments ever attempted. The plan is elegant in its simplicity, yet fierce in its demands. If gravity is truly quantum, then it should be able to produce entanglement between two tiny objects, not through electricity, not through magnetism, not through any influence except their own gravitational attraction. Ordinary matter should create quantum links just by existing. The quiet pull of gravity should reveal a hidden power. The key idea is this: if two masses are placed near each other, and each is prepared in a quantum superposition of being in two possible locations, then each mass creates a gravitational field that depends on where it might be. If the gravitational field itself is quantum, the two masses will become entangled. Their futures will no longer be independent. They will share one combined state in which the geometry of space-time reflects their mutual uncertainty. But if gravity is not quantum, if it remains classical even when matter becomes quantum, then the entanglement will never appear. The two masses would remain separate, and their gravitational interaction would behave like a smooth classical curve with no quantum structure. In that case, gravity would remain a stubborn outsider, refusing to join the quantum family. So we have a test. Prepare two small objects in quantum superpositions. Let gravity act. Check for entanglement. If we find it, gravity reveals its quantum identity. If we do not, gravity may be something fundamentally different from all other interactions. The difficulty is that gravity is incredibly weak at small scales. A tiny particle produces an amount of curvature too faint for any classical device to notice. To make the test work, researchers must protect the objects from every other influence in the universe. Heat must be banished, vibrations silenced, stray photons eliminated. Any unwanted bump could collapse the quantum state prematurely. It is like trying to hear a whisper from across a crowded room while asking every person to freeze in perfect silence. The proposed experiments use small spheres made of millions or billions of atoms, all acting together as one quantum object. These spheres are cooled until their motion nearly stops. They are levitated with lasers or magnetic fields so that they float free from friction. Then, each sphere is placed into a superposition of being slightly left and slightly right at the same time. If gravity responds to each possible location, the gravitational field becomes a superposition as well. The spheres begin to sense each other in ways that cannot be described by classical physics. To detect the resulting entanglement, the spheres are allowed to interact for a carefully controlled period. Then the experimenters bring the wave functions back together and measure whether the outcomes are correlated in a way only entanglement can explain. It is an extraordinary challenge, but the technology is improving at breathtaking speed. What sounded impossible just a decade ago has become a realistic goal for the near future. If the experiment succeeds, the implications are staggering. It means gravity carries quantum information. It means geometry can exist in superposition. It means Einstein's smooth spacetime is only an approximation of a deeper, more granular realm where gravity emerges from the quantum dance of entanglement. To prepare for such discoveries, physicists are building theoretical frameworks that unify gravity and quantum mechanics through information rather than force. In these views, mass is not the cause of gravity. Mass is simply a measure of how strongly a particle participates in the network of entanglement that constructs spacetime. Gravity then becomes the gentle tendency of entangled systems to remain aligned within the geometry they help define. The pull toward Earth's surface would be a collective effect of countless entanglement links, all urging matter to remain part of a shared structure. Even the curvature of space can be seen in a new light. Instead of saying Earth bends spacetime because it has mass, we might say Earth is deeply entangled with every part of the universe around it. The strength of that entanglement shapes the geometry of space so that objects move along paths that minimize disruption to the network. Falling is not a descent. Falling is cooperation with the quantum fabric. This view invites us to rethink what we mean by distance. In ordinary life, two objects appear far apart if many meters of space separate them. But if entanglement connects them strongly, the hidden geometry may place them close. Entanglement becomes a ruler more fundamental than length. The universe decides what is near and what is far based on information, not position. What we call travel may simply be the rearranging of relationships. Gravity might also help maintain quantum unity. When objects become too separated in entanglement space, gravity could act as a gentle tug to restore connection. The formation of stars and galaxies might reflect entanglement networks, reinforcing themselves into rich geometric structures. Dark matter could be entanglement we do not yet understand, shaping cosmic architecture without shining any light. Even the expansion of the universe might signal a change in the density of these quantum links. Perhaps space stretches as entanglement reorganizes, creating room for new relationships to form. If the expansion accelerates, maybe the entanglement network evolves in a way that encourages spacetime to unfold faster than before. The most distant galaxies rush away, not because energy pushes them, but because geometry reshapes itself according to hidden quantum logic. In this picture, the universe grows not outward, but inward, deepening its own structure as new entanglement threads are woven. Some thinkers dare to ask whether consciousness might play a role in this network. Not that the universe thinks in any ordinary sense, but if all matter is connected through information, and if information flows continuously through living systems, then awareness could be a tiny window into the same deep fabric that shapes space-time. Our thoughts would not stand apart from gravity. They would ripple gently across the geometry of the cosmos, small but real. This does not grant magical powers. It does not allow minds to bend spoons or command planets, but it does remind us that we are part of the same entangled order that bends light and shapes galaxies. Our existence is not accidental. It is built into the very architecture of the universe. The possibility that entanglement produces gravity inspires both excitement and caution. Even if initial tests succeed, many questions remain. Does every kind of entanglement contribute to curvature, or only those involving mass? Does geometry respond instantly, or only after signals travel at the speed of light? Can entanglement itself be a fundamental entity, or is it a reflection of something deeper still? We do not yet know. Yet for the first time, we have a clear path to answers. Not dreams, not metaphors, not speculation, real experiments, real measurements made by human hands guided by human curiosity. We stand at the threshold of a discovery that could rewrite the story of physics. What began with falling apples and quantum dice may end with a unified description of the universe, where gravity and entanglement are two expressions of the same truth. Perhaps the universe does not separate the fabric of space from the bonds of information. Perhaps space is what information looks like when seen from the outside, and information is what space looks like when seen from within. The coming years could reveal that every particle curves spacetime, not because it has mass, but because it is entangled. Gravity would then be the most ancient whisper of quantum connection. The universe would be a network of relationships learning how to become a world. The idea that gravity might be quantum is bold, astonishing, and perhaps even unsettling. But science does not reward boldness by itself. Ideas become real only when nature agrees to reveal its secrets through experiment. Mathematics can guide us, imagination can inspire us, but in the end, it is measurement that decides truth. And so physicists have turned toward the laboratory, determined to find the first unmistakable sign that gravity behaves as a quantum phenomenon. The greatest challenge is isolation. In the quantum world, everything wants to interact. Heat, sound, stray photons, collisions with air molecules, even the movement of the Earth itself can ruin a delicate quantum state. To test whether gravity can create entanglement between objects, the experiment must silence the entire universe, except for gravity itself. The masses must be cooled until almost all motion stops. They must be suspended so gently that nothing touches them. They must be protected from any influence stronger than the faint pull of gravity between them. To reach this state, researchers are developing techniques that push technology to new heights. One approach uses tiny spheres held in place by laser beams. The light forms a trap that keeps the spheres floating without friction. Another approach uses tiny mechanical resonators that vibrate so delicately that even a single quantum of energy matters. In both techniques, the goal is to create a system where the entire object behaves as one quantum particle, capable of being in multiple places at once. It sounds impossible, yet progress continues. In recent years, scientists have placed ever larger systems into quantum superpositions. Tiny diamonds containing millions of atoms have had their internal spins manipulated into entangled states. Microscopic mirrors, normally too heavy to show quantum behavior, have vibrated in single quantum units. Even massive clouds of atoms called Bose-Einstein condensates have moved as waves of possibility rather than solid objects. These successes suggest that quantum effects do not stop at small scales. They only hide behind the noise of ordinary life. Silence the noise, and the quantum world steps forward. The proposed tests of quantum gravity build upon this progress. Two small objects will be prepared in superposition. They will hover only a fraction of a millimeter apart. They will feel no force except their mutual gravitational attraction. If gravity is quantum, entanglement will appear. If gravity is classical, it will not. There is no middle ground. One outcome will rewrite physics. The sensitivity required is staggering. To succeed, the experimenters must detect changes in the quantum, states so small that it is almost like listening for the sound of a single drop of rain in a thunderstorm. Technologies such as superconducting sensors, magnetic shielding, and cryogenic cooling are essential. The challenge is enormous, but not beyond reach. Many laboratories around the world are racing toward this goal. Some are building vacuum chambers that remove nearly every molecule of air. Others are developing optical systems that detect motion smaller than a billionth of a meter. Some are exploring new materials that remain stable at ultra-cold temperatures. All share the same vision, a future where quantum gravity is not only a theory, but something we can measure directly. If such experiments succeed, the consequences extend far beyond the laboratory. They would confirm that gravity can carry quantum information. They would show that space-time can exist in a state of uncertainty. They would support the growing belief that geometry emerges from entanglement. And they would give humanity its first experimental foothold on the road to a theory that unites all of physics. But even failure would be valuable. If the experiments reveal that gravity does not produce entanglement, the result would be equally profound. It would mean gravity stands apart from the quantum world and requires a new kind of explanation. Perhaps gravity would then be a fundamental force unlike the others. Or perhaps it would be a phenomenon that emerges from something deeper than quantum mechanics itself. Either outcome would transform our understanding. There are also ambitious plans to test quantum gravity in space. Satellites could carry entangled systems far from Earth, letting them experience weaker gravitational fields and greater separation. Cold atom laboratories in orbit could witness quantum behavior impossible to achieve on Earth's surface. The environment of space may become a new playground for exploring the relationship between gravity and quantum mechanics. Black holes, the most extreme objects in the universe, remain beyond direct experimentation. But with the help of gravitational wave detectors and telescopes that observe the swirling chaos near event horizons, we may catch glimpses of quantum gravity in action. Tiny irregularities in gravitational wave signals could reveal quantum structure hidden in spacetime. The brightness of matter spiraling into black holes could carry codes of information that challenge classical ideas. Even the earliest moments of the universe may offer clues. The distribution of galaxies across the cosmos might reflect quantum fluctuations that later shaped gravity on cosmic scales. If experiments on Earth and in orbit confirm that gravity is quantum, scientists will look to the sky seeking the cosmic signature of ancient entanglement that sculpted the very structure of space. Testing quantum gravity is not only about proving a theory, it is about understanding what the universe truly is. If gravity emerges from entanglement, then the cosmos is not built from matter and energy alone. It is built from relationships. Every object would owe its existence to the quantum harmony it maintains with everything else. Our world would be a web of invisible unity, always ready to reveal its secrets when the noise is quiet enough. Humanity has already measured gravitational waves from stars crashing together in distant galaxies. We have photographed the shadow of a supermassive black hole. We have placed entangled particles aboard satellites and watched their bond survive the curve of spacetime. Each achievement expands the realm of the possible. Soon, perhaps, we will detect entanglement born solely from gravity. That moment will mark the beginning of a new chapter in physics. The age of quantum gravity will not dawn through speculation alone, but through experimental truth. When that truth arrives, everything we know about reality will deepen. We will see the universe more clearly, not as a world divided by scale, but as one continuous expression of quantum geometry. And then we will ask new questions. If gravity is quantum, what does that say about time? About the birth of the universe? About the future of information? About the meaning of connection itself? These are the mysteries waiting just beyond the horizon of discovery. Entanglement can link particles across vast distances, making them behave as if they share a single existence. It is natural to wonder whether such a connection could be used to send messages faster than light. If gravity is quantum, and if entangled particles somehow influence the curvature of spacetime together, could we bend the rules of causality? Could information leap across the universe in an instant? The answer, supported by every observation and every equation we trust, remains a firm and unyielding no. Entanglement does not allow communication. It creates correlations, not signals. When one observer measures a particle from an entangled pair, the result appears random. Only when the outcomes from both sides are compared do the correlations become visible. There is no way for one observer to choose a result and force the partner to see a specific outcome. The universe preserves causality with absolute consistency. Not even entanglement can break that law. This is known as the no communication rule. It protects the speed of light as the ultimate boundary for information flow. It ensures that cause always precedes effect. Without this rule, paradoxes would multiply. Messages could arrive before they were sent. History could be rewritten. The fabric of logic would tear. Instead, quantum mechanics and relativity stand together in harmony, preserving order in a universe that might otherwise dissolve into chaos. Understanding why this matters requires us to look at the structure of information. Information is not an abstract idea separate from physics. It is a physical quantity that must obey physical laws. The speed of light is not simply the velocity of photons. It is a limit that applies to all information. Even gravity appears to obey this speed limit. When a massive object moves, the change in its gravitational field spreads outward at the speed of light, not instantly. This has been confirmed by observations of binary stars whose orbits evolve as predicted by general relativity. So even if entangled particles seem instantly linked, they do not transmit information faster than light. The connection is real, but the communication is not. It is like two dancers performing a perfectly synchronized routine without exchanging messages. Their unity comes from a shared preparation, not a shared signal. Entanglement sets the stage. Measurement reveals the performances, but nothing travels between them. Some have imagined a scenario where gravity might break this rule. If entangled particles share a gravitational bond, could changing the state of one influence the geometry around the other? Could that change be measured as a signal? But again, the answer is no. A gravitational influence that depended on a measurement outcome would require information to travel faster than light. Instead, any gravitational effect arising from quantum entanglement must be as silent as the entanglement itself. Geometry might reflect the unity of the two particles, but not in a way that lets one control the outcome for the other. This silence protects the universe from contradictions. It ensures that every observer, no matter where they stand or how fast they travel, agrees on the order of cause and effect. The no communication rule enforces a deep harmony between quantum mechanics and relativity. They appear different on the surface, but underneath they support each other. This rule shapes the future of quantum gravity experiments. When scientists look for entanglement mediated by gravity, they do not expect faster than light messaging. Instead, they look for subtle correlations that appear only when measurements are compared. The experimenters will not watch one sphere instantly react to a change in the other. They will observe a shared pattern that emerges from statistics, proof of unity, not communication. This distinction is profound. It tells us that entanglement reveals a connection more fundamental than distance. It tells us that gravity reads the structure of information without letting information leak away unlawfully. It tells us that the universe can be deeply interconnected while still respecting the boundaries that guard causality. The silence of entanglement leads us to a deeper question. If entanglement cannot send messages, what is its purpose? Why does the universe allow such a strange phenomenon if it provides no direct advantage for communication? One possibility is that entanglement is not a tool for sending information, but a foundation upon which information is stored. The stability of spacetime might depend on the universal bookkeeping that entanglement performs. By keeping track of relationships between particles, entanglement might preserve coherence in the structure of the cosmos. Look at the world around you. Every atom in your body interacts with countless others. Even when those interactions fade, the quantum history remains. These traces of entanglement do not transmit messages. They ensure consistency. They enforce the rules. They prevent contradictions. The no communication rule is not a limitation placed on entanglement. It is the reason entanglement can exist at all. Even wormholes, those hypothetical bridges of geometry that might represent entanglement, obey this law. The wormholes suggested by the ER equals EPR hypothesis are non-traversable. Nothing can cross them. No signal can travel through them. They are connections without pathways, unity without shortcuts. They preserve the structure of the universe without breaking its rules. This gives us a new perspective on information itself. The deepest connections are often the ones that do not shout. The strongest bonds are the ones that remain quiet. The most fundamental relationships are not the ones that move messages, but the ones that shape reality. If entanglement and gravity are linked, they are linked in a way that respects the sanctity of causality. They cooperate to maintain order in the universe. They reveal that unity does not require communication, and that influence does not require force. And so, the no communication rule becomes a cornerstone in the emerging picture of quantum gravity. It assures us that even as we uncover profound connections hidden beneath the surface of space-time, the familiar rules of cause and effect remain intact. The universe may be stranger than we ever imagined, but it is not chaotic. Its strangeness is organized. Its complexity is disciplined. The cosmos keeps both its mysteries and its promises. In the chapters ahead, we will explore how entanglement might build the shape of the universe itself. We will imagine a cosmos where geometry emerges from quantum information, where distance is defined not by meters but by relationships, where gravity becomes a quiet expression of unity. When we imagine the universe, we often picture a vast darkness filled with distant objects. Stars burn in isolation. Galaxies drift like islands in a cosmic sea. Planets circle suns without ever touching. There seems to be emptiness everywhere, a silence so deep that the nearest star is unimaginably far away. But what if this picture is incomplete? What if the apparent emptiness is misleading? What if everything is held together by invisible ties that do not care about distance? The more we learn about entanglement, the more we suspect that the universe is not a scattering of lonely objects, but a single structure woven from countless connections. This idea challenges the traditional view that space is a stage upon which matter plays its roles. Instead, space itself may be the product of quantum relationships. Entanglement could be the force that stitches the cosmos into one unified whole. Without entanglement, space-time might disintegrate into countless fragments, each unaware of the others. The universe would lose its sense of distance, direction, and geometry. Everything we take for granted would vanish. To understand this concept, imagine two particles created together in a single interaction. Even if they fly apart at tremendous speed, their quantum states remain united. They are not two separate things, but one combined system. Even when they appear to occupy different regions of space, their identity remains entangled. If we push this idea to the largest possible scale, we arrive at a radical claim. The entire universe might have begun in a state where everything was entangled with everything else. As the universe expanded, those connections stretched but never broke. We now observe a space that seems to separate objects, but beneath that appearance remains a hidden unity. Gravity might be the large-scale manifestation of these relationships. It could be the gentle reminder that nothing is truly isolated. Massive objects pull on each other not because of invisible threads of force, but because of shared entanglement that shapes the geometry of the universe. When something bends space-time, perhaps it is really altering the underlying network of information that defines where everything is relative to everything else. This view offers a powerful interpretation of cosmic structure. Galaxies cluster together not only because of dark matter or inertia, but because their existence is embedded in a deeper web of quantum connection. Even distant regions of the cosmos may share correlations that were planted in the earliest moments after the birth of time. The cosmic microwave background radiation seems to carry hints of this ancient unity, a faint whisper from a time when everything was closer and more entangled. It is tempting to think of entanglement as an exotic effect relevant only to tiny particles in laboratory experiments. But it may be the most universal property of reality. Every atom in your body has collided or interacted with unimaginable numbers of particles throughout history. Some of those interactions break entanglement, while others create it. The true state of the universe may be an ocean of connections so vast that no mind could map them, yet so precise that they determine the shape of every star and the path of every planet. This raises a remarkable possibility. The geometry of space-time might not be fundamental. It could be an emergent property that arises from how quantum information is arranged. Distance would not be something that exists on its own. It would be inferred from the structure of entanglement. Regions of space that share strong entanglement bonds would appear close, even if they seem far apart in classical measurement. Regions with weak connections would appear far, even if they are nearby in conventional coordinates. In this picture, the universe becomes a living network. Not a static canvas, but a dynamic system in which relationships build reality moment by moment. Whenever entanglement changes, geometry responds. Whenever matter moves, information redistributes. The flow of time itself may be the unfolding of this entanglement network as it continually rewrites its internal structure. Perhaps space-time is like a tapestry. Entanglement is the thread. Remove the thread and the cloth collapses into loose strands. Add more thread and the cloth strengthens. The universe continues to expand because the tapestry continues to weave. Space grows when new entanglement connections form, creating more room for geometry to express itself. This casts even gravity in a new light. Gravity becomes less like a force and more like a preference for the fabric to remain smooth. Mass and energy distort the network of entanglement, and the geometry adjusts to maintain consistency. We call this adjustment curvature. We feel it as weight. But underneath lies a story of quantum unity, striving to preserve coherence across the cosmos. The idea that entanglement is the true glue of the universe does not undermine the achievements of Einstein. Instead, it deepens them. General relativity describes what happens when the network of entanglement is arranged in a particular way. The geometry he discovered remains real, measurable, and extraordinarily accurate. But entanglement may explain why that geometry exists at all. Einstein saw the shape of the stage. Quantum mechanics might reveal the stitching of its fabric. Even the arrow of time could emerge from the growth of entanglement. In the earliest universe, everything was tightly correlated. As time progressed, the network expanded and complexity increased. The growth of entanglement might define the direction of time, always pushing forward into more intricately connected states. The past would be the memory of simpler patterns. The future would be the inevitable exploration of richer geometry. If this is true, then death is not the end of information. The particles that once formed a living body continue to participate in the cosmic network. Their entanglement spreads outward, merging into the story of the universe. The individual disappears, but the information remains, woven forever into the structure of space-time. Every star that forms, every black hole that collapses, every photon that escapes into the interstellar dark is part of the same network. Nothing drifts alone. Nothing is lost. The quiet bonds of the quantum world preserve unity on a scale beyond imagination. Entanglement also forces us to reconsider the concept of locality. A classical universe obeys the rule that everything only interacts with what is near. Quantum mechanics laughs at that rule. Two particles far apart can share a single description. Distance becomes a practical matter, not a fundamental one. The universe might only appear local when observed at the scale where classical physics dominates. Beneath that appearance lies a global connectivity. It is possible that the reason the universe is stable is because entanglement does not allow cracks. When something tries to separate from the rest of reality, the network adjusts to hold it in place. Gravity might be the visible sign of this adjustment. Everything falls toward everything else, not because of attraction, but because unity must be preserved. If one day a complete theory of quantum gravity emerges, it may describe the universe not as a collection of points in space, but as a web of information. Space and time would be properties that emerge when we zoom out far enough. Beneath that resolution, all that exists are relationships. The recognition of this truth would bring physics back to an ancient idea. Philosophers once believed that separation is an illusion and that everything is connected at the deepest level. Science has long been suspicious of such mystical notions, demanding clarity, testability, and evidence. But now, through the precise mathematics of quantum mechanics and the rigorous experiments of modern physics, the ancient intuition may find scientific validation. The universe does not hold itself together with invisible forces alone. It is held together by the knowledge that every part has of every other part. Spacetime endures because information endures. Geometry exists because entanglement refuses to let the universe fall apart. There is elegance in this picture, a unity that binds the smallest scale to the largest, a harmony that weaves the subatomic and the cosmic into one continuous song. And yet, there is mystery. How did the entanglement originate? How does the universe decide which connections matter and which ones fade? What lies beneath the network itself? We approach answers, but the final truth remains veiled. In the next chapter, we will explore what it means for the universe to know itself. If entanglement connects everything, then perhaps the cosmos is not merely a stage where events unfold. Perhaps it is an observer of its own structure. Perhaps knowledge, consciousness, and the shape of reality all emerge from the same quantum glue. The journey from the smallest particles to the largest galaxies has always revealed the same surprising lesson. The universe is more connected than it appears. What seems empty is woven with subtle bonds. What seems separate is part of a deeper unity. Now, as we explore the relationship between gravity and quantum mechanics, that unity becomes impossible to ignore. Entanglement stretches across space. Geometry bends around mass and energy. These are not separate processes. They are two ways the universe ensures that information never stands alone. If entanglement shapes space-time, and if gravity emerges from that entanglement, then the cosmos is more than a stage for existence. It is an active participant in shaping itself. Every quantum connection changes geometry. Every geometric change influences the way matter interacts. The universe continually learns about its own structure. It continually updates the relationships that define reality. This insight invites us to rethink what it means to observe. In classical physics, an observer is merely a bystander who measures what already exists. But in the quantum world, observation is an act of participation. The universe does not reveal a pre-written script. It reveals possibilities shaped into facts through interaction. Knowledge is not separate from existence. It is woven into the very act of being. When a particle is measured, its quantum state collapses into one definite outcome. That collapse is not only a discovery by an observer, it is an update to the network of entanglement. The structure of space-time responds. Gravity subtly reshapes itself to reflect the new information. A measurement is not a glance. It is a conversation with reality. Every interaction leaves a trace. Every trace becomes part of the cosmic architecture. Even consciousness may be tied to this process. Not that consciousness controls the universe in a mystical manner, but living systems gather information, preserve it, and act upon it. They are places where entanglement becomes organized into patterns we call thought, memory, and identity. If the universe is a web of information, then consciousness is an intricate expression of that web. Our awareness is not separate from the cosmos. It is one more way the universe understands itself. This does not diminish science. It anchors science more firmly than ever. Human minds are made from atoms forged in stars. Our neurons communicate through quantum processes. We are part of the same network we observe. When we study gravity and entanglement, the universe is studying itself through us. Physics becomes a mirror. In that reflection, we see not only distant galaxies and subatomic mysteries, but also our own origin. We are made of information preserved from the earliest moments of time. The atoms in our bodies once floated freely in primordial plasma. They became trapped into molecules, then into cells, then into living organisms that could ask questions about the universe. Curiosity is not an accident. It is a property of a universe that creates observers to witness its beauty. If gravity and entanglement are linked, then the evolution of the cosmos becomes a story of information structuring itself into complexity. In the beginning, the universe was simple. It was hot, dense, and nearly uniform. As it expanded and cooled, tiny fluctuations formed. These fluctuations grew into galaxies, stars, and planets as gravity helped organize matter into stable structures. Life emerged on at least one world. Intelligence grew. Consciousness awakened. The universe developed the ability to reflect upon the relationships that hold it together. This perspective gives new meaning to the idea that the universe knows itself. Knowledge is not only written in equations, it is written in the structure of spacetime. It is written in the entanglement that binds particles across cosmic distance. It is written in the thoughts of beings who look outward and inward with equal wonder. Entanglement teaches us that nothing is isolated. Gravity teaches us that everything influences everything else. Together, they reveal a universe built on connection. A universe where separation is an illusion created by scale. A universe where every particle plays a role in shaping the totality, even if that role is impossibly small. The fabric of reality is stitched together by the constant exchange of information, forming a tapestry richer than any picture we could imagine. As we imagine the future of physics, we can see many paths for discovery. Experiments may soon confirm that gravity generates entanglement. New telescopes may detect signs of quantum geometry in the sky. Mathematical breakthroughs may finally form a complete theory that unites quantum mechanics and relativity without contradiction. When that day arrives, science will take its boldest step yet. We will understand not only how the universe behaves, but why it has the shape it does. Perhaps space and time are not fundamental at all. Perhaps they are stories told by information. If so, then the universe is telling a story of increasing complexity, increasing awareness, and increasing connection. Our presence is a chapter in that story, and our search for knowledge is how the story continues. It is comforting to know that the cosmos does not waste anything. Information persists. Entanglement persists. Even when stars explode and galaxies collide, the relationships that define reality continue to evolve. Nothing is erased. Everything contributes to the ongoing structure. The death of one form becomes the birth of another. Gravity does not let the universe drift apart. Entanglement does not let it forget what it once was. To gaze at the night sky is to witness the grand network of existence illuminated by distant fires. Each point of light is a node in the cosmic web. Each photon that reaches our eyes brings ancient information carried through the geometry of space. When we understand that those points are connected by more than emptiness, the sky becomes a map of unity, a reminder that we are part of everything we see. If the universe is a single entangled system, then its destiny is tied to the preservation of connection. Stars will fade, galaxies will spread apart, but the information held in the fabric of spacetime may continue to evolve, forming new patterns even as old ones disperse. Far in the future, long after the last light has dimmed, entanglement may still bind the remnants of reality into something coherent. The universe might never lose its structure, because that structure is information itself. Gravity shapes the universe. Entanglement connects it. If the two are one, then every particle is a thread in the cosmic fabric that holds reality together.